Hi everyone, good morning. So we're here at the Agda meeting, but as you might know, there's other proof systems as well.
Really?
Like Lead was mentioned, or Cock, or others, and even things that are not based on time theory. I've heard these things exist as well. Yeah, this talk is about making the connection between Agda and these other systems, because they have proofs and we would like them, or we have proofs and they would like them, making them more interoperable. At the same time, this talk is also maybe a bit more practical, so this is about how to implement a backend, and that's something I would really like to encourage everyone to do more, right? Building a backend for Agda is really nice, and you can do lots of fun stuff with it. Finally, it's also, there's definitely connection also with what Phil talked about, because in order to translate from Agda to other languages, we need to go through a kind of a core language, and so part of this work is also very much connected to finding, well, what is actually the core language. Okay, so here's the overview of this talk. So I'll first talk a bit about what is this EuroProofNet and what is Deducti. Then I'll talk about encoding of Agda's base theory, or the sort system in Deducti, and then about this backend, so the Agda to Deducti itself, so which translates like your Agda files to Deducti. I'll talk a bit about, well, issues we're still having. So there are some features that are a bit challenging because of, so universe polymorphism and ETAC quality. We have time and some conclusions at the end. So let me get started. So what is EuroProofNet, if you haven't heard about it yet? So it's a European cost action. So it's a network of researchers working on improving interoperability and usability also of proof systems. And proof systems here is really like a very broad definition, so it includes both proof assistants, but also like automated theorem provers, and even like model checkers and such. We're also considering those. It's quite big, so I mean, it's easy to join, so it's maybe not as impressive as it looks, but there's like 300 researchers from 40 different countries, and if you want to join, you can. So you can apply on the website, which is EuroProofNet.github.io. You will get updates, and you will get invitations to come to the various meetings. And this whole huge thing is kind of centered around the tool Deducti, which is kind of not a proper proof assistant by itself, but it's meant to be an intermediate language for translators, so that we avoid the quadratic overhead. Like if you have 100 systems, you only need to implement 10 translators instead of 100 for each of them to each other. Yeah, so that's a very brief introduction to EuroProofNet. So then what is Deducti? Well, it's first of all, it's a logical framework. So in the tradition of like Aleph or Alf or yeah, I mean, there have been a bunch of them. So that means it's a system for encoding other theories or systems in it. It's meant to be used as a meta language, and it's based on the lambda pi calculus. But the unique thing is that it relies heavily on high-order rewrite tools to encode computational behavior of theories. So you can use it as kind of a way of checking or transforming proofs. So in particular, we can use it to as a way to double check the output of the main prover. So I think this is actually an interesting application for Agda also, because we don't have a core language at the moment, but we can use this as a way to double check the output of the main type checkers. If there's any bugs, this catch them. And also, yeah, like I said, it's used as an intermediate language for translation. It has a quite small core is deducti, right? So it's not meant to be, like, it's not super user-friendly, I'll show you later. But the advantage is that it's easy to implement, like an independent implementation. That's also important, I think, because it allows you to, I mean, even implement your own checker if you don't trust the checker that you got from GitHub. It's makes it quite easy. And there's currently 3 different implementations with various goals. Yeah, there's already encodings of many different proof assistants, such as Coq, Isabelle, Matita, and also some other proof systems, which I hadn't really heard of.
What's the difference between a proof assistant and an other proof system?
Okay, so I guess they're not used in the same interactive way as a proof assistant. So they're more automated. So it's more like so this modulo is kind of based on this event B method. If you've heard of that, it's set theory based. Yeah, so I haven't.
So many of these are completely automatic rather than interacting with users.
Yes.
Okay.
It's well, yeah. And
is it also that the proof assistants are the ones you've heard of? And
yes. Yes. So it's. I would say it's also just a question of a different community, I guess, and a different set of priorities and motivations. Yeah, but yeah, it's like maybe one of the goals of this EuroProofNet is also just to make us aware of actually there's other people as well doing proofs in a sense, but not in our sense perhaps. And there's interesting challenges, right, in translating between those two, because it's not what we're used to. But, I won't go into that too much. I do want to, I will show a bit of deducti on the slide, so I do want to do a very quick tutorial on deducti, and I'll do the simply type lambda calculus without a base type. So this is how deducti works. So you can declare new constants. So here I'm declaring a type of types of the calculus, and then I'm declaring a specific type of arrow types. Right? So far so easy. Then we need some terms as well. So this is dependent type, right? So for each type, or for each type, we want to have a type of terms in that type. So this is intrinsically typed. So type the term, and then we can do term constructors in the high-level abstract syntax style. Right? A lambda takes a function that from terms of type A to terms of type B, and it constructs a term of this arithmetic. And then we can already define some examples. So this is the identity function. So everything is explicit, so we need to annotate everything like super explicitly with both the domain and the codomain of the arrow type, but otherwise this looks. I see some confusion. Does this make sense? Yeah.
This doesn't have, by design, this doesn't have any hidden arguments?
Yes, indeed. So this is one thing. Yeah, there's no hidden arguments here. They have a layer on top that's called lambda pi, which does have hidden arguments, and it elaborates to this thing. But this is it's part of like it being a very small core thing, so it doesn't have any inference of implicits.
I'm guessing because it's supposed to be a target for machines.
Yes, very much, yes. And then we can also define symbols with rewrite rules. So here, for example, I want to define the application, right? So this is going from the other way, right? So we have a term of type arrow AB, and we want to apply it to a term of type A. But now I also define a rewrite rule, right? So that application of a lambda to some argument reduces to. So this is defining the beta deduction for the simply type lambda.
So that UV in brackets at the front is like for all U and V?
Yes, so you have to explicitly say what are the pattern variables of this rewrite rule. Yes.
And could you give types for U and V, or is
You
that?
can, yeah, you can. But, so this is optional, you don't need to, but...
Okay, so when you say it's based on higher order rewriting, what you mean is you can declare rules like this one.
This is not really doing high order rewriting yet, I would say. I can give some examples of that as well, but this is just the
Yeah,
first
I'd love to
overview.
see an example of the higher order stuff.
But maybe yeah, it's not really essential for the talk, so maybe I'll show you later. If you're interested in that.
Yes, but sorry, is that def app, is that the type, or should app be another constant? Or-
No, so, no, def, yeah, so you need to declare it as a def if you want to add rewrite rules to it.
Right.
If you don't use the def keyword, it's assumed to be a constant that's like a constructor basically. So if you want to rewrite it, you need to do that. And then yeah, you have this colon equals is kind of a shortcut for defining a symbol and a rewrite rule that is.
So normally when we declare constructors, we do it in a data declaration.
Yeah.
We say, here are all the constructors at once.
Yes. So this is not like that, so that you get less guarantees, like you don't get any guarantees for completeness, for example, right? So you can always extend your types with more constructors, nothing preventing you from doing that. And then this is part of it being really a meta language for defining your actual language in, right? So this is, yeah, it gives more flexibility at the cost of less safety.
And the pattern matching does not happen in the definitions, but only happens in the rewrite.
Yes, indeed.
So, but for the rewrite rules, this is like the Edinburgh logical framework from 1987. Or what is in the 12 system in
Yes. Oh yeah, so 12 is based on like more logic programming. I guess so this is you replacing that with rewrite rules.
But 12 just has these constant declarations like
Yeah.
I, arrow, term.
Yeah.
So, but about this rewrite rule, so this has this magic underscores.
Right. So the underscores are just pattern variables that I didn't mention.
So it does some kind of type reconstruction for.
So there is some interesting part there. So there is some checks on the rewrite rules. That these are well typed, right? But it's not. So it doesn't check that the pattern is well typed, but it checks that it assumes that the pattern is well typed, and from that it tries to prove that the right-hand side is well typed. So you can actually write seemingly ill-typed rewrite rules, but like as long as like the right-hand side is well typed, assuming the left-hand side is well typed. So it's more general than rewrite rules in Agda in that sense. Okay. Yes.
So before you said that if you translate Agda to the dictate, it somehow like gives you additional safety for Agda.
Yeah.
But then in the dictate you can kind of type anything. So I guess what you mean is that you have an additional.
Yeah. So the idea is that you first define a deductive file with a bunch of constants and rewrite rules in it, which defines the theory of your language, right? And then the actual translation, so when you actually translate a concrete Agda file or file or whatever to deductive, then it's only produces definitions in the ideal case. But I'll come back to that a bit. So that you only will have this. You're just defining new terms that make use of this theory, but don't add any new constants or.
By definition, you don't need def.
I mean the thing with the column equals, so where you just define alias. But we're not quite there yet.
Yes, you said it was using higher order abstract syntax, but the function symbol for the argument to lam is not different from the other function symbols. So is it really a full function space where you can do case analysis on the input, or
No.
do you have any guarantee?
No, no, so it's a logical framework, which, yeah, so this is a much weaker function space.
Right.
Yeah, you cannot really analyze the structure of this term, right? You can only use it as a variable.
So the only pattern matching you can do is in the rewrite rules. You
Yes.
cannot define functions.
Yes, you can only do pattern matching at the top level, but not like in this
Right.
function.
So when you say def ID block colon equals block,
Yeah.
is that the same as saying def ID colon its type,
Yeah.
and the second line that says ID
Rewrites to.
rewrites to?
Yes, exactly.
Okay, so the colon equals just an abbreviation for a rewrite. Okay.
Indeed. That's my one slide deductive tutorial. So now you know all deductive. So, and recently there was a nice work I wanted to mention. So, theorem for the system at EuroProofNet in Paris, they translated some rather big library from Matita to Agda via deductive. And this library in particular includes proofs of Bertrand's postulate and Fermat's little theorem. And as far as they said they were not done, so as far as they were not proven in Agda yet, so this is kind of a good sign that this is actually useful. And also this was not really trivial because Matita is an impredictive system, so they had to do some transformations on the proofs to make them predicative before they could export them to Agda. So, I mean, it's still like very much all of this is work in progress, but it can already save us some work.
And how do they translate it, like proof?
Read their paper.
Okay. What I mean is it usable? Or
Is it nice?
yeah,
It's a good question.
right.
I guess it's usable and unreadable.
Yes. So, yeah, so I haven't looked at all the details yet.
Okay.
And then, yeah, so what this talk is about is, well, we want to connect, be able to do this with Agda proofs as well, right? So suppose we have some proofs that other people want to use, we need to be able to export Agda proofs to deductives, right? And in order to do that, we first need to encode the basic logic of Agda in deductive. And then we need to have some translator from Agda files to deductive files. And that's this
The previous translation from that web didn't go through deductive?
It did, yeah.
It did. Okay.
But there we didn't need to translate from Agda to deductive.
So deductive to Agda works?
Well, I mean, you have to read the paper again, but there were still some things that needed to be done by hand, or like it's very much prototype. At least it was less work than writing the full proof by hand. So yeah, let's get started with that.
10 minutes.
10 minutes, okay, great. So I'll just see. Oh yeah, sorry, before I go to explain the next, I was going to ask, okay, so suppose we want to encode Agda, like the core theory of Agda, where do we start, right? What is the first thing you need when you need
A core theory of Agda.
Yeah,
What does that include?
yeah, what is the first building block that you put in your building?
Oh, the source.
Typos.
Sorts, yes. So in particular, the universe levels. The most important part of Agda, taking your time when doing this exercise. So here's just a very simplified version of it, where we don't have universe polymorphism, but just complete levels. So we have level 0, and we have a successor, and then we have a maximum operation, events. Right? So that's the first step, and then on top of that we can define the sorts, right? So, and then there's the first challenge maybe, which is that Agda uses Russell-style universes. So that means that if you have an element of a universe or of a sort, then that element itself is a type, and that you cannot do that in deductive. So deductive uses Tarski-style universes, and that means that if you have a type or an element of a universe, then you can interpret that. So you have to have some function that interprets this element. And so this is just like explaining why there will be a bit of extra overhead in the next slides. Which, and there's good reasons for this, but it makes deductive simpler at cost of making the encoding a bit more So yeah, so where do we start? Well, we want some sort system, so we define a new deductive type of Agda sorts, right? And then, well, for now, let's just assume we have a sort set for each level. All right, set L. So that's what we need. Then, well, we need to also say, well, each of these sorts, we need to interpret it as the type of its elements, right? So this U. So this is the thing that's needed because of the previous slide. So we need to interpret each sort as a type. And then finally, yeah, if we have an element of this U of S for some sort, then we also need to interpret that thing as a type again. And that's this L. So we give it a sort, and we give it an element of the universe associated to that sort, and then we get the type of its elements, or goods terms. Yes? So this is great, so there's still a problem with it, right? So this gives us, for each sort, a deductive type of its elements, but it doesn't yet give us any Agda terms, right? So we just have types, but there's no terms in them yet. And the first term that we will add are, we want to have internal universal as well. So we want to have set I as an Agda term. And set L is now a sort, it's not a term. And so for this we need to get, well, to the first part of this pure type systems that Phil mentioned also, right? So we need this the axiom rule of our pure type system. So we need to know for each sort what is its successor, or what sort does it belong to, and this is, since we only have set I, we just get set successor of I, and then we want to internalize that, right? So for each sort we get a term of type or of this universe axiom S, and then we identify the elements of this terms with the universe S. I'm not sure, like, how.
Okay, my
more
brain.
explain it, but I'll let you stare at it for 10 seconds. And,
The axiom definition corresponds to what we call univ sort. Then.
Yes, exactly. Yes, but yeah, I guess I wanted to use a bit more of the standard terminology from pure type systems here, but.
The axiom is not a function, so it's still a bit confusing. Axiom is the relation, and you.
Right. Yeah. So here it's a functional pure type system. In the sense that we always have exactly one. Okay. I'll share the slides if you want to stare a bit more later. And then we want to have function types. Now that we have universe function types, and for that we need the rule of the pure type system, right? So for each two input sorts, we want to have a sort of the pi type. So the sort of this pi type when we know that A is in S1 and B is in S2. And this sort rule S1, S2. And that's just taking the maximum of the two universe levels. And then we can add the product constant. And so it's a bit verbose again because the product here takes 4 arguments because we need to give the two sorts explicitly. But actually, this is also the case in the internal syntax of Agda. We're also annotating these pi types with their sorts. So this is not that different from what's happening in Agda. And then finally, well, we can now do a lot of complex encoding, but actually a nice trick is we can just identify the elements of this product type with deductees function type. And this is basically doing, again, what I did before, so doing the high-level abstract syntax. Right? We're just defining functions in Agda to be functions between the types of the elements in deduct. So that's like the core theory of Agda, right? That's the basic part we need to set up in order to start translating any Agda terms. And now we can do do some translations. So this is going to be a bit more practical, right? So this is Agda directly is implemented as an Agda backend. So it means it uses the Agda compiler as a library. And this allows us to reuse many parts of the Agda implementation, such as the internal syntax representation and the type checking monad, which has a lot of useful stuff in it. And yeah, so this was the rough structure of Agda's type checker that Andreas also showed yesterday. So this is the linear pipeline, and then what we do with Agda to the deductee is kind of branch off here. So we don't use the treeless syntax, but we just go directly from the internal syntax to deductive.
Also, you don't want to compile clauses, but simply or do you use the original clauses?
I'll come back to that. And then, yeah, so this is the internal syntax that I'm sure you all know, but I gave like a version of this slide before, so I wanted to show this. This is like Agda's internal syntax. So there's like variables, lambdas, missions, file types, sorts. Don't care, but don't care about it. And then this type checking monad has a bunch of very useful operations. So I listed a few here that we're using in the backend. So we can get information about defined symbol, as we get const info. We can get information about built-in primitives of Agda. We can get information about the context, so about the bound variables. We can add things to the context, right? So add a new variable to the context and locally. So this kind of doing this TCM operation in an extended context and then reload it again. We have like an internal double checker, and we can have this equals to parameters, which I'll explain on this slide maybe. Yeah. So we need to kind of, in deductive everything needs to be explicit. In Agda, we often erase some arguments, so to constructors. Okay, move this slide. Okay. Okay. So anyway, we have to use these reconstruct parameters to reconstruct some. Also, I'm running out of time. So, okay. And then, yeah, we can translate terms. So here's the basic shape of the translation. So it's a very one-to-one translation of the basic syntax. So variables are mapped to variables, defined symbols are mapped to defined symbols, etc. So for the PyType, we need to do a bit of extra work, right? We need to get sorts of the codomain. But actually, these are already present in the internal syntax. And then the universes, we just need to insert this U construction. I see you laughing.
I like the sort of A, sort of E.
No, we have an internal Agda function that's called sort of also. So that's the one we're using. Sort of. Okay. And then, yeah, coming back to your question, so for data types and constructors, we just define translating to constants, right? And that's how they work in Vecti. So if you have not, then we translate these to be constants, right? So we have an element of this universe and elements of not, and an element of the product type, not to not. So an alternative way to do this would be, which would maybe be better, would be if we had a kind of a universe of data types and we just picked out the code for not. But so far, we're still having to extend the deductive theory. Basically, each time we introduce a new data type. So in that sense, yeah, we're not checking everything that we should check, but we're just postulating that this is a good data type. So we're not checking positivity here, for example. We're not checking that it is. But this is, but.
So will deductive let you write stuff that's not positive?
Yes. Because it's
so
not.
deductive you can write terms that loop forever.
Well, there is a separate termination checker, which is not like you need to run it separately on your deductive file. So you can check termination, but it's optional.
Does that mean that deducti makes it easy to construct a proof of false?
Yeah, so deducti is not meant as to be a theorem prover, right? It's meant to be a logical framework in which to implement your theorem prover. And then you use your theorem provers to check the actual proof. Yeah. And that's why I'm saying that this is actually not the right thing to do, right? Because we're extending the theory itself here, while we would really want to just produce a term in this theory, but so far we don't do this.
Okay.
Yeah. And then, so for definitions about pattern matching, yeah, we just take the clauses in Agda and translate each clause to a rewrite rule in deducti. And again, this is like, yeah, not, we have to, with each definition, we're extending the theory. And so again, there's some ongoing work. So Tiago Felicissimo was trying to actually kind of implement my PhD thesis, do this translation. It's, I guess, it's not easy to implement, or it's a lot of work. In theory, it's all there, but yeah, in practice, there's a lot of things to get right. Yeah.
In the ideal situation where we have Agda in the does that mean the entire code base of Agda in the rewrite?
No, so this is really just, we would only need the Agda core, right?
Yeah.
Most of the Agda implementation is not necessary for just checking the core language. Like, most of it is just like inferring implicit arguments or like doing parsing and scope checking, and this is all not needed yet.
I guess that matching is also something that probably not needed.
Yes, so that's a good question. Whether, I mean, you want to have some form of pattern matching, but yeah, probably not like not in this form. At least, like, we would rather have something like case trees instead of clauses. Okay, so I think I'm going to skip through most of section 4, but so these are two things that we're currently still, like, we have some solutions for encoding universe polymorphism and E-type quality, but they're not really satisfactory at the moment. So I guess the main takeaway is that they are, because this is mostly because of limitations of deducti, and so we're, like I was a few weeks back, I was at the deducti implementers meeting, first one, but they were very much inspired by what we were doing at the Agda implementers meetings. And then we discussed like, what can we do to improve deducti to support this. So universe levels, yeah, we have. So basically, one sentence summary, we need some rewriting modulo associativity and commutativity because this maximum operation. And so for that, we need a non-linear rewrite rule, and you can do that in deducti, but it's kind of it breaks confluence, so you end up with a less usable system, I guess. Having a better way to do this natively. And then we have E-type quality in Agda, so for record types in particular. So, and in particular for the unit type. And this is fun. So if you want to check that two terms are convertible, you cannot compare just their normal forms because they might both have the unit type. And then they're equal even if they don't have the same normal form. And so there's a bunch of solutions, but so that are either not stable under substitution or introduce some nonlinearity, or require you to annotate every term with its type, which is like, I mean, works in theory, but you get huge terms. And then, yeah, so the idea is to extend deducti actually with some kind of type-directed conversion. So the core of the problem here is that deducti uses untyped conversion, and this is like what I there's a very nice paper by Agda and Andre on it's a type theory or a framework for type theories with extensionality rules. So you can take a look at that paper. So to complete, so a summary, so many parts of Agda can actually be encoded quite directly in deductive. You can just define symbols to constants and clauses to rewrite rules. It's not completely satisfactory, as I explained. You can do it. And then other features like reconstruction of constructed parameters, critical theory for universe levels take a bit of work. We have a way that works now. And then, yet other features we don't yet have a good solution, like this E-type. Some future work, but I'll just let you read this and let you ask questions, or just not ask questions, and we can go to the coffee.
Thank you.
Thanks.
The coffee won't get cold, so I think we can.
You already know what the question is. What about cubicle?
Yes, Go talk. So there was Bruno Balas. He's working on this.
Sorry?
He was at the deductive meeting, and he's working on, it's very early work, but he is actually thinking about how to encode cubicle stuff in deductive. But I'm not involved in that myself. But there is, there are 6 working groups within this EuroProofNet thing, and so I'm part of the one that kind of tries to implement the translators for languages that we already know how to encode in theory, but we don't know how to do it in practice yet. I mean, although some of these things are actually, we don't even know how to encode it in theory. But, and then there's another working group that is working on like type theories where we don't have a good idea of what the encoding would be. There's, you can take a look at the website. There's, there's a Zulip also. So I think that's working group 6 probably. Ask some questions there because there's definitely people interested in this. Yeah. Guillaume?
So you said you were translating clauses to rewrite rules,
Yes.
but in Agda you have a first match semantics, and in deductive it seems to be like any match will fire the rewrite rule. Right? So do you have to do a bit extra work?
So we have a solution for that actually. So we have the coverage checker in Agda computes a new set of clauses which have been unoverlapped basically, right? So you don't use the original clauses that the user wrote, but the clauses that are computed by the coverage checker, which are not overlapping.
Is that what you needed though?
Yes.
Right.
And there was a pooling. I mean, so there's now I added a flag actually that because normally they're like computed and then thrown away again by the coverage checker. But there's a flag now if you want to keep them. So for the backend like this, you can enable this flag.
Could we use them during type checking? To have the typical catch-all clauses?
No, because you can use them, but it's kind of you cannot. I mean, they're exactly the same computational behavior as the case tree. So, and we also only get them at the same time as the case tree. So there's not much.
So it's already too late.
It's already too late.
Right. Okay.
Since you worked on rewrite rules for Agda, are there any lessons to be taken from the Dart itself?
Yeah, I think the most interesting thing that we don't have is this. The non-well-typed rewrite rules in the sense that are the condition like having this. If the left-hand type is well-typed, then the right-hand side is well-typed. And that's like, in Agda we currently have both types have to be well-typed and have to have the same type. So that would be. Otherwise, I think it's very similar. Well, in Agda some things are more complicated because of E-type quality and in elements.
But how would this work in Agda? Why would you ever have a non-well typed left-hand side?
I mean, basically, so the reason why they have it in Deducti is similar why we have dot patterns in Agda. Right? So you know that a certain argument that argument has a certain value, but it's not a pattern, this value, so you cannot write it in the pattern. So you just write an underscore, right? But then and then this is not, so you can write rules like that also with rewrite rules in Agda, but it will still check that this term is equal to the given term each time, even if it's like completely useless to check this. Even if we know from the typing already that it has this value, we're still checking, so we're still doing useless work basically. And so I think there Deducti has the nicer approach that they actually avoid doing this useless work. And then also, it's a bit like, I think they also have like more efficient evaluation of rewrite tools, which I guess also would be nice to have in mind.